stage of development is a descriptive theory is built on correlation. The more data sets you get, the more cases you look at, the better quality correlations. Does that make sense? So, normative theory, prescriptive, it's like these are little correlation matrices. Okay, no correlation here, there correlation. Right? Building prescriptive theory. Prescriptive theory means I prescribe what you can do and what you can't do. It's all about, constantly refining the categorizations, and the theory gets better as the categorization gets refined. So do you think, so let me ask you this about anomalies. If you have a theory and you have anomalies, is anomaly a good thing or a bad thing? Say, why do you think it's a bad thing? He thinks it's a bad thing. People agree with him? You agree. You think it's a bad thing. Why is an anomaly a bad thing?
It can feedback to adjust the model.
Yeah. So you're saying it's bad, but because it allows you to adjust the model?
Yeah. In the beginning.
Yeah.
The more abnormal you can feedback to change the theory.
All right. So is that a bad thing or is it a good thing?
In the first stage, maybe it's good.
The first stage it may make you look stupid, so it's a bad thing. But I would argue that actually, and I think you basically said this, anomalies are actually a good thing because they allow you to refine the theory. That's what you just said. Because as I cycle around this theory pyramid, I can refine my theory. I can, so actually, the more anomalies I find early on, the better I'm going to be at building the theory. Okay, and then as I look at more and more companies, right, the number of anomalies should go down. Right, as I build a bigger collection of stuff, and in the end, that's what a lot of case research is about. One of the things, I'm jumping ahead a little bit, we're looking at a lot of semiconductor companies here because the semiconductor industry is in Taiwan, right? A huge part of the world industry is in Taiwan, so it's actually very convenient. We can drive out the back end of campus here and do lots of case research on semiconductor companies and not have to spend a lot on gasoline to drive right from. Very, very convenient. And the more you look at and the more strange situations you look at, the more it can help you refine the theory. And that's, in essence, what we're doing here. Okay. So with that background, okay, I'm now going to give you a little more perspective on case. And I should pass around this since it's been sitting here. And there's, I'll pass this around, and you can play with it. There's a button here in the middle, which with all the applications are at the bottom. Okay, so you can click on those. And this is the OLPC X01. You'll notice that you can turn it into a game player if you want. And these are the wireless antennas. But I figured. I asked JC, should I bring it along? He says, oh, yeah, we're a developed country, so we don't have these, so we can pass it on. But and take a look at it. And so now let's talk about this case. Right? What are we trying to teach? This is generally in the context of the course. I'm going to try to give you a little bit of perspective on this particular case. Most courses using the case method have a series of cases grouped into modules. Okay? And what we were trying to do is we were trying to do two theories in this particular case. One is modularity theory, okay, and one is disruption theory. So I'm going to give you a brief discussion on modularity theory, and then I'll give you this discussion on disruption shift theory. Just maybe 10 charts on modularity, a few charts on disruption, okay, because I'm going to hopefully change the way you look at this case. So, what's the motivation for modularity? Modular systems, and this is actually a very important issue for Taiwanese companies. Okay. And you'll see, hopefully, in a bit. What's the motivation for modularity? When I have a complex system, a big, complicated problem. If what I can do is cut it into smaller problems, right, then I can solve smaller problems independently, right? And, you know, this beyond the capabilities of one person's hands or minds, I can kind of partition the problem into little pieces. So if I can divide the system into multiple parts so multiple people can work on it, then I overcome this limitation of everything has to be done by one person. When I move from simple to complex, the point at which something can no longer be made by a single person, you know, modularity enables division of labor, right? You do this, you do that, right? Or we'll set up a production line or design line. When something can no longer be comprehended by a single person, it's another good reason. So a lot of reasons for modularity. Now, I don't think very many of you remember this era. You know, I think when this computer was running, I was maybe about 4 or 5 years old. Okay, but early computer systems, it was very interesting. IBM was a leader in early computer systems, and they were monolithic. This is a picture of the 7030, which was a very large computer system in the late 1950s. That meant everything about them was unique for that system. Right? So a design team would build everything, including the central processor, the printer, console, and you know what? Every computer IBM made had a slightly different instruction set. The revolution that IBM introduced, which actually revolutionized the industry as well as IBM as a company, was to introduce System 360 in 1964. And they said, you know, these computers have gotten so big and complicated, we have to cut it into parts, break it into pieces so that we can understand it. So they started by introducing multiple levels of modularity. For example, there was a simple building block. This was a very early, not an integrated circuit. It's a couple of transistors and capacitors on a ceramic module with pins. Right? It was called solid logic technology instead of vacuum. Okay, so there was one level of modularity. They had certain types of these things, and then they had these cards where, you know, there were standard types of cards. I could plug in one of these here or one of another one. There were only certain types of cards. These are like the NAND gates, basically, or, you know, registers and things like that. And, you know, when you look at a modular system, it can be instituted by creating, designing, enforcing a set of design rules. Right? So design rules mean everything at this particular edge obeys these rules. Here are the physical dimensions, electrical characteristics, or whatever. You know, you can have hidden modules where, you know, anything that I do inside doesn't matter, or you can have a visible module which says, you know, even though this is a module, people next door have to know what's inside it. Okay, that's just kind of interesting. So once design rules are set, an interesting thing happens. Right? Because it's all modular, you know, I actually get an explosion of options. Like, for example, cars have this modular property of the tires, right? You know, the rims are always the same size, or they're always the standard size, so I can buy tires from multiple manufacturers. Okay? So I get an explosion of options, and within each one of those modules, I can get competition. Right? Economists talk about tournaments where, you know, one supplier will win or another one. So you're starting to get a flavor of the industry here. Okay, so in terms of IBM System 360, they said, okay, we're going to have these global design rules, you know, processor microcode, you know, they had all these design rules that said, here are the standard pieces. Okay, and they only actually had a few very simple design rules. Number one, every system will have the same machine length, the same instruction set. All I/O devices look identical except for the speed. Single method of memory CPU coupling, single I/O control structure.